Hello everyone, welcome to the sixth video of our lecture series. So in this video, I will going to discuss about how to calculate bound state of any given potential. So first you have to know what is bound state. So let us recall what is bound state for classical case. So suppose we have a potential of this kind. And suppose and we have a particle here, and this particle has energy value this is our energy value, and this is our potential graph as a function of x. So if initially the particle is here, then it will only be allowed to move in this region. So it will not be able to go here or even here. Even if the energy, even if the potential here is less than the energy, but as the particle is initially here, so it will not be able to go here. So the particle will be bound in this region. So this is This is the case of bound state for classical particles. Now suppose we have quantum particles. So now suppose that this particle is now a quantum particle. So what will be the case? Like in case of classical one, it will not be able to go from here to here. But in case of quantum, if the particle is quantum, then there is always a finite probability of tunneling. So even if the energy in this region we have potential to be greater than energy, but the particle will be always a finite probability for the particle to go from here to here. So for quantum mechanical particle, V is greater than E. That is not a sufficient condition for bound state. So what will be the condition? Now we have to have the potential at infinity to be greater than E. So in that case, we will call this we will call that the particle is in bound state. So this will be true bound state, because at infinity we have potential greater than the energy. So there is not a probability of tunneling. So for quantum mechanical particle, for bound state condition, we have to have the potential at infinity greater than energy. No, so now suppose one condition, or let us take a potential of this form. So suppose we have a potential of this kind. We have V0 for x less than minus a by 2. We have 0 for minus a by 2 to a by 2. And we again have V0 for x greater than a by 2. So let us draw this potential. So this height is V0. So you can see that at x tends to plus minus infinity, we have potential to be V0. So what should be the energy for bound state to exist? We must have energy less than V at x tends to plus minus infinity. So that means we must have energy value less than V0. So that is the condition for bound state. So for in the given potential, we have to have energy somewhere here. So suppose this is our energy of the particle, and which is less than V0. So now let us calculate what will be the number of bound state for different width of this well and different height of this potential well. So let us proceed. So first we will write down our Schrodinger equation in all three regions. So let us call this one as region 1, this one as region 2, and this one as region 3. So let us write down the Schrodinger equation in region 1 and solve it. So we have minus h square square by 2m del 2 psi del x square plus v psi is equal to e psi. So what is the potential in region 1? It is V0. So we have my h square by 2m del 2 psi del x square. So 2m by h square. V is V0 here minus e psi. And what do we have? We have E less than V0. So if we denote this term as K1 square, so K1 square is 2m by h square V0 minus E. So that means K1 square is positive. So we have del 2 psi del x square equal to K1 square psi. So what will be the solution of this equation? It will be, so suppose a e to the power K1x plus suppose constant g e to the power K2x minus K1x. So now what does this psi represent? We know that psi square represents probability of finding the particle, or thus whatever the system it is. So in region 1, if we put x tends to minus infinity, then we can see that this term, it will diverge. So that means probability of finding the particle will diverge. So this is not physically possible. So we can discard this term. So what is our solution in region 1? So our solution is a e to the power k1x, and it is for x less than minus a by 2. So similarly, if we solve this in region 3, and if we apply same logic that the probability should not diverge at x tends to plus infinity, then in region 3 we will get there will be another normalization constant, and we will have here we will have minus k1x. So that is the solution in region 3. So let us call this as psi 3 for convenience. Psi 3 is d e to the power minus k1x, and that is for x greater than a by 2. So now solve in region 2. So if you look carefully in region 2, we can see that the potential in region 2, that is symmetric. That means Vx and V of minus x, this is equal. So we know that if the potential is symmetric, then the wave function must be even or odd. So that is a very powerful statement. So let us prove this. Let us prove that if the potential is symmetric, then we will have wave function to be either even or odd. So let us write down the Schrodinger equation first. So we have our Schrodinger equation here. And now, if we change the variable x from, so we change x to be minus x, and so now you can see that del 2 del minus x square, it will give us del 2 del x square. So if we write this in by changing the variable, we will get minus h cut square by 2m del 2 psi minus x, we have changed the variable, plus v of minus x psi of minus x e psi of minus x. So we get h cut square by 2m del 2 del x square. Now potential symmetric means v of minus x should be v of x. So by changing the variable, we are getting this equation, and we already know that Schrodinger equation is this. So if psi x satisfies this equation, then we can see that psi of minus x also satisfies the same equation. So from superposition principle, we know the Schrodinger equation satisfies superposition principle. So that means if psi 1 is a solution and psi 2 is also a solution, then their linear combination is also solution of the Schrodinger equation. So from superposition principle, we can write that psi of plus x, if we denote a combination of these two, so let us write this as psi of x plus psi of minus x, and let us write another combination, so psi of minus x, which is psi of x minus psi of minus x. So you can see that this is an even function and this is an odd function. So we can say that from superposition principle, these both they satisfy Schrodinger equation. So we have proved this, that if the potential is symmetric, then we have a solution of the Schrodinger equation which is either even or odd. So now let us write the Schrodinger equation in region 3, in region 2. So in region 2 we have potential to be 0. So we can write the equation as E psi, because our potential is 0. So let us write K2 square as 2me by h cut square. So, and in region 2 the wave function is either symmetric or antisymmetric, that means either even or odd. So we can write our solution in region 2 to be either B cos K2x, or we can write as C sin K2x. So that is for even n, and that is for odd n. So in n means different states. So for ground state, second excited state, fourth excited state, we will have this wave function, and for first excited state, third excited state, we will have this wave function. So what is our complete solution? So we have solution psi ax, so that means antisymmetric or odd. So that we have as a e to the power k1x, that is for x less than minus a by 2. We have c sin k2x for x minus a by 2 to a by 2, and we have d e to the power minus k1x, and that is for x greater than a by 2. And we will have another solution which is symmetric or odd or even. And that will be like this. So that is our solution of the Schrodinger equation. Now we have to use boundary conditions or continuity conditions. So what is the continuity condition? Continuity condition states that psi 1 at x equal to plus minus a by 2 must be equal to psi 2. So for psi 1 we will have this only minus. So that is a continuity condition. We have another condition as at psi 2 at x equal to a by 2, it must be equal to the psi 3 at x equal to a by 2. And we will have continuity condition of derivative of psi. So it will be psi 2. So what does this derivative of psi continuity condition? It is that psi 1 derivative at x equal to minus a by 2 must be equal to the psi 2 derivative at x equal to minus a by 2, and we will have psi 2 derivative at x equal to a by 2. It must be equal to the psi 3 derivative at x equal to a by 2. So let us consider the case for x equal to minus a by 2 for psi a. That means for the antisymmetric wave function. So what will be the condition of this? So we will have a e to the power minus k1 a by 2. It must be equal to minus c sine k2 a by 2, and from the derivative condition we will get k1 a e to the power minus k1 a by 2, which will be equal to the k2 c cos k2 a by 2, because we are taking derivative of sine. So from these two we can write k2 cot k2 a by 2 equal to minus k1. So if you do the same like at x equal to a by 2 for psi a, we will land with the same condition. That means k2 cot k2 a by 2, that should be equal to the minus k1. So that is our first condition we get. Now let us do the same for the symmetric case. That means for x equal to minus a by 2 for psi s for symmetric wave function. So for symmetric wave function, if we do the same type of calculation, then we will get k2 tan k2 a by 2, which will be equal to the k1. So that is our second condition. So now these two, it is not easy to solve them directly. So we can either solve them graphically or numerically. That means we can solve 1 and 2 either graphically or numerically. Now let us suppose that we have alpha n square, which is k2 a by 2 squared, so which is m a squared e n by 2 h cut squared, and let us denote r to be m a square v0 by 2 h cut square. So if we put this one in first condition, so what we will get? So from 1, so one condition we have k2 cot k2 a by 2 is equal to minus k1. So if we put this, then this k2 a by 2, this is an, and so from here we will get minus alpha n cot alpha n, which will be equal to r square minus an square, and that is for the odd wave function. And similarly, if we do this for symmetric wave function, then we will get alpha n tan alpha n, which will be equal to r square minus alpha n square. So that is for the even wave function. Now the solution of these two, this function and this function, are given by the points where this circle of radius r intersects with this function and this function. So what are the when we will get the solution? So the solutions So why I am calling this a circle? So suppose alpha n is our x coordinate and we have our y coordinate to be root over r square minus alpha n square. So alpha n is our x. So if you can write this as r square. So this is an equation of circle. So when this circle intersects with this function or and this function, then we will have our solutions. So let us draw this. So this is, let us change the color. So this is our alpha n axis, and we have our y value here. So let us draw the circle for different r. So for different r, we will have circles of different radius. So let us draw a circle first. So this will be a circle. This will also be a circle. These are for different values of r. So these are circles. And now if we plot this one and this one with respect to alpha n, then we will get, so this 0. This is suppose pi by 2. We have our pi here. So suppose this is 3 pi by 2, this is 2 pi, and so on. So what will be this function? Alpha n tan alpha n. So it will be like this. So let us change the color. So this will be asymptotic to pi by 2. Again, it will be asymptotic to 3 pi by 2. So at pi it will be 0 and it will be asymptotic. And similarly from 2 pi to it will be like 5 pi by 2. It will be asymptotic. And if we draw that alpha n part alpha n, so we will have like this. So at pi, so it will start 0, from pi by 2 it will be 0. Similarly at 3 pi by 2 it will also be 0. And we will have like this. So this is our alpha n part alpha n, and this is our like alpha n tan alpha n, and this is our circle of radius r for different values of r. So this is the graphical solution for finite square wave potential. And they are given, so they are given by the intersections of root over r square minus alpha n square with alpha n tan alpha n and minus alpha n cot alpha n, where alpha n we have as so alpha n we have m square en by 2h square and r square is given by m square v0 by 2h square. So this is our solution of this finite squirrel potential. Now the number of solution, that means number of bound state, it will depend on the size of R. So we know that R depends on A and V0. So as A increases, it will lead to R increased, R will also be increased, and also if V0 increases, it will also lead to R increase. So that means the deeper and broader the well, the value of R will be larger, and hence the number of bound state will be more. So the deeper and broader the well, the value of R will be larger, and that is why the number of bound states will increase. So now we have R in a range such that, like, we have V and A in such range for which we have R 0 to pi by 2. So if R is from 0 to pi by 2, then we will have only at least one bound state. So if our radius is here, then we will have one bound state. Now if our radius is like for any value, we will have only one bound state. Now we have our radius to be this. So this, if this is the case, then we will have one and another one here. So we will have two bound state. Now if we have R value for which we have this circle, then we will have this one, and this. So number of bound state will be here 4. So in that way, as R increases, as this radius increases, we are having more intersections. So that is how we are getting more bound state. So suppose, so in this range, if R is 0 to pi by 2, then we will have V0 will be this. So V0 is less than this. So if the potential is like, so in question you may have to calculate the value of the potential, the range or the maximum value up to which there will exist only one bound state. So you can do in this way, and similarly you can be asked for like when we will have 3 bound state. So we will have 3 bound state when R will be in this range. So in that way you can calculate the potential depth, the depth of the potential, and also you can calculate the how much broader the well should be, for which we will have a definite number of bound state. So that is how you can calculate number of bound state. So this is for finite squirrel potential. So potential, we may have different kind of potential profile, but the procedure is same for every problem. So here we have a potential barrier. Also we can have a potential dip or something like this one. So this is minus, suppose minus a by 2, and we will have potential 0 everywhere. So that can, so the concept is same. You have to do the problem in similar manner, and either graphically or in this way, you can calculate the strength of the potential, or how much the D, or how much the broader the potential well or barrier should be, for which you will get a definite number of bounce state. Okay, so that is it for today's lecture. So we will meet on our next lecture video.